Greetings. In understanding and learning how we find different properties of different materials, we started with two alternatives. The first alternative was perfect gas. And when we talked about perfect gas, we defined it as a gas that follows PV equals RT. And this way, we said that if we have two properties, um, two intensive properties, either P or V, or T2 of these three was enough to calculate the third. Now, the other alternative that we used was to use saturation tables. And that was when our material was not a perfect gas, and we could use saturation tables. It was very close to phase change. It was either liquid or vapor or solid. And it was changing phase. And what we did was to learn how to find their properties from different saturation tables. A very good example of a perfect gas was air, where in many cases, air could be assumed to be perfect gas. And a very good example of saturation tables, material that we could use saturation tables to find its properties, was water. And for water, we had ice, we had liquid water, and also vapor. And it, these two, air and water, are very common materials for many thermodynamic processes. So, but uh, there's an alternative case where we neither have perfect gas nor we could use saturation tables. And we don't know which one to use still. Of course, water and air are very simple cases, well known. But in other cases, like the example I'm solving this time, we have ethane. And for ethane, we don't know if it's perfect gas or not. Can we use PV equals RT or not? And what you have to do is to learn how to calculate different properties for ethane. Now, the alternative for us is to use this compressibility chart. So if our material is not a perfect gas and doesn't follow this equation, then perhaps it would follow PV equals uh, RT, but with a correction. And the correction we're looking at here is PV equals ZRT. It means that there is a correction here, Z, which they call it compressibility factor. They call it compressibility factor. And what it does is that it's a factor which basically corrects our assumption of the perfect gas. And they have tested many substances for it, and they have come to a chart where it gives us the possibility to calculate or to find Z. So in a simple case, Z equals PV equals RT, and there are two parameters which we should learn before we can calculate Z or read Z from this chart. One is reduced pressure, PR, which PR equals P, the pressure divided by P critical. It is the pressure divided by critical pressure, and that is called PR, reduced pressure. The other parameter that is of interest to us is TR, which equals T, which is temperature, divided by T critical, the critical temperature. And a knowledge of these two parameters, which are shown in this figure, PR is here, and the TR are these lines. You see, it's written here, TR equals 5, and then we have all other values for it, which is 2.5. These are these solid lines here. This is 2, 1.8, and this is 1.6, and coming down to TR equals 1. You see that PR and TR are both 1 is the critical point. Now, so this table basically helps us to read Z from this table and learn um, how do we correct our perfect gas law. So with this chart, we are able to use PV equals ZR T. There are other lines on this chart as well. And if you look at them, they are VR constant, reduce specific volume. And their values are, say, from here, start from here is 0.2 and then continue to 0.25 and 1 and more. These are the dashed lines which you see moving in this direction. It's important to learn what the definition of VR is. It's very different from PR or TR. For VR, there's a different definition, and that is the specific volume at any point, the real value of the specific volume, divided by the value of a specific volume if the critical point was perfect gas. Interesting. That's how it's defined. So if you know some substance, you know the critical temperature and critical pressure, or you know it. So this is a constant value for every material, for every substance, and you just divide the real value of V specific volume, and then you would have VR. Or alternatively, if you have a VR from any means, then you can calculate V, the real specific volume, from this equation using these values on the chart, and that's what we should do in this example. Well, the problem tells us that there is ethane, and which is a gas, of course, and we don't know if it's perfect gas or not. Its pressure is initially P equals 10 megapascal, and its temperature T equals 100 degrees C. So these are our initial condition, and let's call them P1 and T1. Now, it undergoes a constant pressure process. So the process is constant pressure process. There's a constant pressure process. So anywhere, wherever it is, P2 equals P1, and that equals 10 megapascals. So we have everywhere, whatever process that happens to other, but wherever the end point is, still its pressure is 10 megapascals. But it expands, ethane expands, and V2 equals 1.6 V1. Its volume increases 60%. Its mass remains constant, so it is basically a Consider it as a cylinder piston arrangement, and its mass remains constant, constant mass, constant mass, but volume is increased up to 60%. And now the problem tells us, what would T2 be? What would T2 be? You see, uh, there are two methods to calculate this, and the question asked us from is, either we could calculate it from PV equals RT, which is a perfect gas assumption. We don't know if it's a good assumption or not. Or we can calculate it from PV equals ZRT, which is the more correct way of doing it. And once we have done both cases, then we would learn how accurate this one is, or how the real value of different parameters are from PV equals ZRT. Well, our first step is to go to the tables and see what do we know from ethane from tables, regardless of the process that happens to it. These are the properties for ethane. And this is the table I used from the book by Senja, and it appears early in the tables. And what we learn from these, well, ethane appears here, ethane appears here. Its composition is ethane is C2H6. C2H6 is the composition, and its M molecular weight M equals 30.070 kilograms per kilomole, and then R equals gas constant is 0.2765 kilojoule per kilogram Kelvin. These are these two values, 2765. And then here we have the critical temperature and critical pressure, which is critical temperature is T critical equals 305.5 Kelvin, and P critical equals 4.48 megapascal, and finally V critical equals 0.1480 cubic meters per kilomole. These are our general knowledge about ethane, regardless of whether we assume it perfect gas or not. If we assume perfect gas, then our calculation would be very simple. How do we do that? You see, for initial condition, which is here, for initial condition of assume perfect gas, assume perfect gas, and what do you get? At its initial condition, P1 V1 equals M1 R T1. This is what happens from this equation. At this final condition, initial condition, which is here, this is our equation. And at its final condition, after the constant pressure process has ended and its volume has increased 60%. What you have is P2 V2 equals M2 R T2. These are just perfect gas law for initial and final condition. What does this? It relates just two specific properties to a third. Now, between the initial and final conditions, P1 equals P2 and M1 equals M2. We assume that not to change. And therefore, for between these two conditions, I mean, I'm just working on properties, okay? I'm just working on properties. I haven't forgotten my basic way of solving the problems, but I have assumed just the system of ethane and its properties are these. Now, mass remains constant, so M1 equals M2. Pressure remains constant. And therefore, V1 over V2 equals T1 over T2. And therefore, T2 would equal 1.6 T1. And that would equal 1.6 times T1, which is 100 degrees C. And it would be 100 degrees C. We have to turn it into Kelvin. Remember that. It would be 373.15, and the outcome for T2 is 597.04 Kelvin. This is our result for a perfect gas assumption. Remember, it's very important. This is what a perfect gas assumption would tell us for the final condition. So I would write it here with perfect gas assumption. With perfect gas assumption. Okay. Well, I shall solve the rest of this problem for the real gas in the next video. Thanks for watching and cheers.